In yesterday's lecture, we saw the basic aspects of how to do parallelization, correct. We discussed this Jacobi program or the stencil program, where we talked about the dependencies and how parallelizing it in different ways, right. Either you break some of the dependencies and therefore be able to parallelize, or you do them in some order, right. This is basically what we discussed in yesterday's lecture. We are going to continue with that. Okay, maybe for the next 20 minutes or so, I will talk about it in a very generic way, and then the rest of this lecture will be again divided into two parts. In the first part, I will do a quick introduction to OpenMP programs, and in the second part, I will do a quick introduction to MPI programs. Again, I will try to deal with some very basic aspects of OpenMP and MPI and try to show you how you can write parallel programs using OpenMP and MPI, but writing programs in either of these interfaces, okay, would still involve you following all of these parallelization principles. That is really the idea. Okay. So, how many of you do recall the program that we saw yesterday with regard to this stencil computation? You remember? Only two? Oh, few. Only few. What about the others? Many things got overwritten in your memory in between? Okay. So, it is a simple program. It has an n by n, right, kind of a matrix, and what we do is that for every grid point, we essentially take the average of all of its neighbors including itself, and we write it back into that particular element in place update, correct. And last thing that we do is that we see what is the difference between the previous value and the current value, and we sum it up over all the grid points and then see if it is greater than certain threshold value or less than some threshold value. If it is greater than certain threshold value, we continue to iterate on this. This is basically the computation that we perform, and there is a dependency from the left neighbor and the top neighbor. Okay. Those two will actually use the new values which are computed, whereas the right neighbor and the bottom neighbor would use the old value that they have computed. But we also have the insight from the application that if we do not follow this dependency very strictly, then also the program will converge, but it may take more number of iterations to converge. That is the insight, or that is the knowledge that we have from the application. So, we saw one particular version which is what is called the red black version, where we do all the red point computations and then followed by all the black point computations, and we said that yes, when you are doing the red point computations, you are ignoring certain dependencies, but then eventually those dependencies will get added because of your repeatedly doing these iterations for convergence. Okay. Today, we are going to see a different kind of doing this computation. We are going to talk about doing this assignment, where we are going to talk in terms of a group of rows together, okay, as a task. That means that within that group of rows or block of rows, I am going to do the computation sequentially, right. So, I have this large matrix, I am going to divide it into multiple blocks of rows, okay, and within each block, I am going to do the computation serially. That means that there I am going to respect all the dependencies that were originally there, correct. But across these computations, across these blocks, okay, at the iteration level, at the iteration level, what I will do is that I will not obey the dependency, but across different convergence iterations, I will bring back the dependency. Okay. I will show you how it is being done. Okay. So, here is a shared memory version of that particular program. We will skip most part of it, we will only pay attention to the parts that we need to spend time on. So, I have highlighted them in red. You can see that this variable, which is the array where the data values are there, is a shared variable. Diff is also a shared variable. There is something called a lock that I am going to use, and there is something called a barrier that I am going to use. This may not be the exact syntax, but we do not care. We just want to have some understanding. So, the language in which you are going to write is going to provide you the correct syntax, and you will follow that syntax. Syntax is not all that critical. I am going to actually leave the rest of the stuff which is more like initialization. So, let us not worry about it. Somewhere here we say that we have to create a number of processes, and each of these processes need to do this routine called solve. That is essentially what we are saying. So, I know that I am going to do this domain decomposition, and in this domain decomposition there are going to be number of processes, okay, and each of these processes will do one block of computation, correct. They will do one block of computation, compute my difference value, sum of the differences, okay, and then pass it on, somebody else will compute the global difference and then tell me whether we have converged or not. If we have not converged, we have to go back and redo this computations again, I mean do these computations iteratively. That is really what it is. So, let us skip most of this part and then go to the next slide, which actually talks about solve. As I mentioned earlier, I am not talking about the red black version, I am simply talking about a block of rows. So, for example, let us say if I have 1024 rows and I want to divide this into 4 processes, I can say the first process can do the first 256 rows, the second process can do the next 256 rows, and so on and so forth, correct. So, I do that kind of a computation somewhere over here. Okay. So, yes, okay. So, let us just start off from here. So, my begin would tell me for that particular process which is the beginning row and which is the ending row, okay. So, if it is process the second process, it will start from 257 and go to 512. If it is a third process, it will go from 512 to whatever that number is, right. Like that we will declare that. That part is fine. So, what I am going to do is that, so this is essentially where I am computing what is my begin and what is my end, basically dividing the number of rows, okay, equally across all of them. Okay. Then there is this convergence loop, which basically says while we are not done, keep doing things. And then we are going to initialize these two variables, and remember diff is a shared variable, my diff is a local variable. I am going to initialize both of them to 0 and all processes are executing this. You may ask, why should all process execute diff equal to 0? It is enough if one process executes it, because it is a shared variable, but there is no harm in all of them writing, provided you make sure that they finish writing before somebody starts updating this diff value. Okay. Okay. Now, there is this barrier statement, and a barrier statement essentially tells that all processes which are executing must come to the barrier statement, and only when all of them have come to the barrier statement, they can go to the next statement. So, this is a place where they all synchronize. That means that all of these processes must be executing these statements in whatever speed or whatever way they are executing, right. And once they come to the barrier, they will check whether others have come, correct, and only when all others have come, they will start executing the next set of statements. So, that is a barrier synchronization. Is that clear? Right? We all agree that we have completed everything before that. Now, we are doing the barrier statement, and after that we will again continue to execute the other things. Once they start executing the loop, they may be executing it in different speeds, we do not know, correct. That does not really matter, because whenever there is a requirement for a synchronization, the programmer will put the appropriate synchronization. That is the reason why we put the barrier here. They may be executing these statements in whatever speed or whatever order they want, right. They all have to execute it in program order, that is fine. But then what I am trying to say is that one processor could be fast, one processor could be slow for whatever reason it is. By the time they come here, they may come here at different points in time. But you have to ensure that all of them have completed this execution before you start this next instruction. Okay. Now, this part of the code is very simple. You can see that they are going to do it for the block of rows that have been assigned to them, and they are following all the dependencies that you want. That part of the code is very nice. Okay. What we do not know is that when I am talking about, let us say, the 512th row, right, that 512th row will take values, old values of the 513th row, new values of the 511th row, and so on. That new values are taken because that is being done sequentially. Okay. Again, look at the 256th row. The 256th row has to take the new value from the 255th row. That may not necessarily happen here. We may break that dependency for a while, right, because I cannot guarantee that the previous process has completed the new value for 255. I say, do not worry, you go and take whatever value that is there. Okay. So, every process as far as its top row is going to concern may or may not necessarily get the new value, but it will still work on it. And again we are going to rely on the fact that the convergence will eventually take care of it. So, let us not worry about that particular dependency. Okay. Now, what happens is that they all compute for all the rows that have been assigned to them, and they also compute what is called a local diff, which is what is called my diff, where they are kind of trying to find out what is the absolute difference between the old value and the new value, and they add it up. So, if I have 4 processes, there are 4 copies of my diff, each having those difference values for those blocks of rows. Now, I have to sum it up together and then see whether that has met the convergence condition. So, for that what I do is that I do this lock and then I do the addition and I do the diff. So, remember yesterday also we talked about this, whenever I want to do some kind of a reduction, I have to allow one process to do this. So, here I am going to assume that one process is going, here I am actually saying each process is doing, but it is doing it in a critical section. Why in a critical section? Because I have now locked it. So, they can access the old value of diff, add the new value of my diff, add the value of my diff to it and then write it back into diff, and when they are doing it, no one else should see the value of diff, Diff has to be updated atomically, correct. So, that is ensured by putting these 2 lock unlock statements here. It may not be exactly in this syntax, but we do not care, whenever you use a different programming environment or an interface, whatever is the appropriate one, you will put it there. So, this ensures that diff gets updated properly. Here we are implementing the critical section, or we are updating diff atomically. Any doubts about that? That part is clear? So, that is needed, because if I do not have this lock unlock, what would happen? 2 processes may read the same value of diff, and only one of those my diffs will get added to this, the other my diff may not be written back. To avoid that only we need to put that. Again after this we put a barrier statement. Again we have to ensure that all processes have completed this. Notice that because we have put a lock and unlock statement here, if there are 4 processes, each one of these processes is going to execute this one after another in some order. Maybe process 2 will execute first, then process 1, then process 3 and then process 4, whatever order it is, we do not care, but they will all have to execute that one after another, because this is a critical section, After this we have a barrier. This ensures that all processes have completed all of these activities and they all have updated the diff value. Now, I can see whether my diff satisfies my tolerance condition. If not, I am going to if it is, I am going to set the done variable, which is also a shared variable, to 1. And then each process kind of continues. Again all processes update done, that is also fine. And then again I continue on this. Now, one question that you may want to ask is that why do we have these 2 barriers? What would happen if this barrier is not there? What would happen if this barrier is not there? This barrier is probably easier to see, correct? What would happen? Supposing let us say if this barrier was not there, then the first process which went into the critical section would take that value of diff, compute this and may decide a wrong decision, may take a wrong decision, correct? That is not what you are supposed to see. You have to ensure that all of them have updated diff before you check the tolerance condition. But because it went into the critical section first, whichever process it is, it can run and then do this statement. That is why you want to stop it by putting a barrier over there. By putting a barrier over there, you are ensuring that all 4 processes have completed this operation and the diff has been updated correctly. Yes, sir. Correct.
Local thread stack variable.
Correct.
And the diff is the variable which will be
shared variable. Shared variable.
But you have declared my diff before and diff inside this my.
Does not matter. No, this is a private variable. This is a shared variable. Correct. I have set both of. I am setting both of them to 0. That is all. In my declaration, I would have. I think in the previous slide, if you see, right. In my declaration, I have set shared variable float, shared variable diff, which means that my diff is local, right, private. Okay, again it depends on the language. One language would say one way, the other language would say other way. We don't care about it as long as we understand that my diff is private, local to that particular thread or process, correct? Okay. So, that part is fine. So, we understand why the second barrier is there. So, what about the first barrier? Why is it there? So, if I make sure that if this barrier is done, then everybody computes the convergence condition correctly, then they can go ahead and execute this. What is wrong in this? Right? Why should I put a barrier here? Remember, every time I put a barrier, I am asking the fastest person to slow down, correct? Why should I put a barrier there? Huh? The diff will get? This diff might get executed, and then if this diff comes after that, it will make it 0. Okay, that shouldn't happen. So, you have to ensure that that does not happen. Okay, good. So, look at the code and then try to understand what it is trying to do. Okay, so this is how the shared variable is shared memory program is going to be, and as we saw that the interaction among the processes happen because due to these shared variables and whatever conditions you want to derive out of that. Okay. After the first convergence iteration is done, when you go to the second convergence iteration, right, remember we talked about this row which is above. For example, let us talk about process 2, which is supposed to calculate the rows from 257 to 258 and so on, right. In the first iteration, it was calculating for 257, it was not taking the new values of 256, right, it was taking the old values. But by now, it would have got the new values because we have done a barrier synchronization and all the things that you saw so far with regard to coherence and consistency would ensure that the new values would be now seen by all the processes, correct. Therefore, when you come and do the second iteration process 2, when it is trying to access let us say I minus 1, right, it actually refers to the latest value of the 256th row, grid points in the 256th row. Okay. That is really how it is happening, and that is how, right, you are now sharing data across these different processes. Is it clear? Okay. Now, instead of doing this using this kind of an operation, okay, lock and lock, one could also do it using a reduction operation, okay, reduce or something like that, which will automatically do what you have been doing, perhaps with less overhead than what you have seen. Okay. So, that is essentially what we are going to see in terms of a shared memory program as a generic thing. Okay. We move on and then go to message passing version. In the message passing version, when I talk about this n by n grid, I cannot think of it as a shared data. Why? Because there is no provision for a shared data. It is a distributed memory program. So, first of all, I have to now think in terms of either my blocks of rows as individual private arrays in each one of these processes, okay, and they operating on that. That is the first thing that I have to do, because I can't think of this as one huge array of n by n, because there is no common shared memory, there is no shared address space. Okay. So, you can't declare A to be a global shared array, right. And when you are going to declare it as a private, there is no need to declare the entire array, because you are going to work only on a block of data. You can declare only that part of it as you want. Okay. So, you are going to write a program which is structurally similar. They also use the word SPMD, which stands for single program multiple data, which is essentially domain decomposition that we are talking about. Okay. Here the orchestration is going to be different. There you are thinking in terms of putting these barriers and synchronizations to make sure that they are accessed in an appropriate order. Like for example, you had the lock and unlock, correct. Whereas here there is no notion of a shared variable, but still you may need certain synchronization, you may need some collaboration, interaction among these processes. How do you ensure that? You will ensure that by means of some communication, and if it is required, you will also put some synchronization. So, let us see how this is done in the distributed memory. So, we will define something called a ghost row. I will actually show you what it is. So, this is my original array, Okay, I am going to divide 3 rows per process. Okay. So, essentially that means that each one of the array will have a copy or will have in its memory those 3 rows. But in order for you to compute this, you also need the top row and the bottom row. And where are the top rows and bottom rows? For this, the top row is this blue row and the bottom row is this red rows, correct. Those are what are called the ghost rows. Okay. So, you essentially divide this array in such a way that these 4 rows goes to the first process, these 4 rows go to the second process, these 4 rows go to the third process and so on. Okay. Of course, there is a gray grid point here which I have not shown, but let us not worry about it. Okay. So, that is essentially what is happening here, maybe something is not copied properly, okay, or maybe that is happening in animation. Okay. Now, you see, right. So, now each process has this much of data, 5 rows of data, even though they are supposed to process only 3 rows of data. Okay. That is the 2 ghost rows are being added to it, right. Now, initially you will declare the array, you will initialize the value, this may happen in one process, and after you have initialized this value, then what you need to do is that you need to send part of this array to each one of those processes. So, let us assume that process 0 is responsible for initializing this array, and after it has initialized this array, it is going to keep this part to itself and then send this part to process 2, this process to process 3 and this part to process 4, right. It will keep sending these things, and those processes will receive this data from process 0, this data process 1, this data from process 1 and this data from process 1. So, by doing this send receive commands, mapping send receive commands, those processes will actually get the data values in their arrays. Then of course, they will do the same computation that we have seen, iterating over all the grid points sequentially, okay. And at the end again this process will communicate this row of grid points to the previous process, it will communicate this row of grid points to the next process, and it will receive this row of grid points from the previous process and this row of grid points from the next process, and these are the new values. Okay. And once they have received this, again it can go ahead and do the computation, that is one part. The other part is to check the convergence condition. So, convergence condition again can be computed, because each one of you are going to compute the local diff, and then you can send the local diff to maybe process 1 to do the global diff. Process 1 can tell you whether convergence is met or not met, and it can send a message which all of them can receive and then decide whether to go or not go. So, that is exactly how the program is going to be. So, let us see, again I am going to skip the initial part which is not very interesting. Let us look at this part, okay. It kind of continues. Okay. So, let us say actually this is where the interesting part is, this is where the arrays are getting communicated. So, you can see that if my PID right is not equal to 0, then I am going to do something. If my PID okay. So, it is a little bit more involved. So, let me not go into all of these details, okay, but I will tell you what exactly is happening. So, okay, maybe we should spend time. Okay, so maybe we should spend time on this, but we will come to it after we finish the iteration part. Okay, let's look at this here. Okay. So, inside that iteration, what we are going to do is that once I have my data values, I am going to start from 1 to my end, because each one has some fixed number of rows, right, 256 rows or whatever it is, and it is going to do the computation for that many rows, and it is going to do for all the column elements. It is going to do exactly the same computation, it is going to find out the absolute difference, it is going to add it to my diff. Okay. So, this part of the computation is fairly straightforward. Okay. After it has computed that, then what it is doing is that each process except process 0, which is the very first process, okay, is going to send my diff to process 0, and it is going to receive from process 0 the done variable. Okay. So, essentially what you are doing is that we have computed the local diff, I am going to send it to process 0, so called the process 0, who is going to compute the global diff as well as tell me whether we are done or not done. Process 0 on the other hand, okay, is going to receive data, okay, from each one of these other processes, okay, and it will get basically the temporary diff data and it will actually add up all of them. Okay. It will add up all of them and it will do for all the processes, it will compute the convergence condition and to all processes it will actually send that particular done flag. Okay. So, this is how the communication happens. So, everybody computes the local diff, sends it to process 0. Process 0 receives all of these local diffs, adds them up to its global diff, okay, computes the done condition and sends the done condition. Yeah. That part of it I will come to it. Okay. That part of it is the previous thing. Okay. All right. So, you see that dot 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 thing over here. Okay, that is the one that we are now going to do, because if I have started off in the first iteration you would have been confused. So, now everybody has computed from their first row to last row. Now, they have to communicate those first row and last row to the neighboring elements as well as receive something from the neighboring elements. So, let us see how that happens. Okay. So, you go back to the previous slide, okay, except for okay, let us look at okay. So, yeah, let us look at this. So, each process except process 0, okay, is going to send its first row, okay, 1 comma 0, its first row, okay, to the previous process PID minus 1, right. Each process except the last process is going to send its last row, my end, okay, to the next process. Right, because the first process and the last process, right, do not send their top rows to the previous one and similarly this does not send the bottom row to the last one. Okay. That is the reason why these if conditions are there, but otherwise essentially you are sending the first row, you are sending the last row, first row to the previous process, last row to the next process. The last argument here. Row. Okay, that is some kind of a tag. Let us not worry about it for the time being. Okay, it is a tag. Basically, every message will have a tag, and the corresponding receive should use the same tag to map it. Okay, you can use wildcard, which means that any send can be mapped with any tag, but that is a programmer decision. Okay. All right. So, this is the size of the variable, this is the target to which it has to be sent to, and so on. We will when we talk about MPI, I will specifically talk about these things. Okay. All right. Now, if I am not the first row, then I must receive both my top row as well as my bottom row, ghost rows I have to receive, right. If I am not the last row, last process, right, then I have to receive both the top rows and bottom rows. The last process will not receive the bottom row from last plus 1, there is no last plus 1, right. So, it cannot receive. Similarly, the first process will not receive anything from that's on the top side. So, except for that you will receive all of them. You receive them and put it in 0 or my end plus 1. Okay. So, that is the ghost row. So, now you have got all of these things, the new values have come, correct. So, you see that this is the while done loop. Okay. Now, you are saying that my diff is initializing my diff, you have received all the new values and you are now ready to do this computation. Okay. So, the data exchange has happened, okay. The accumulation of values into diff has happened, the communication of done has happened, okay. All by using synchronization, sorry, messaging, yeah. Sure.
How does the process differentiate between whether the receive is the first row or the first ghost row or the last ghost row?
That is a good question. Okay. So, if you see, right, it is going to say receive from PID minus 1. Okay. Any message that it receives from PID minus 1 is going to be for the first row. Okay. Any message it receives from PID plus 1 So, let us think of one particular process, let us say process 3, right. When process 3 receives a message from process 2, it is always the last row of process 2 which has to be your 0th row, right. When process 3 receives a message from process 4, right, it is for your last row. So, that is my begin plus end. That is how you oh, here is it, correct it, please correct it. That is an exercise, yeah, sorry. Okay, so, you got to really, so that is essentially what it determines. I think I must have cut and pasted, but not corrected it properly. Good point, alert, right. But the idea is very clear, right. We are still not very sure about the syntax, we are still not sure about many of these things, but let us not worry too much about it. We just want to get the concepts clear at this point in time. Are the concepts clear? Okay. So, this is essentially what we have talked so far. Okay. So, in the message passing version, the communication happens, in terms of full rows, because you want to pack all of these messages and send it together, which will actually reduce your overhead. Okay. The code looks similar to what we have seen earlier, but interaction happens through messaging, synchronization also happens through messaging. So, if you look at in this previous code, there is no barrier, there is no global barrier. Why? They are not, no, that has nothing to do with sharing. There is really no need for you to synchronize everything like what you did in the case of a shared memory program. All that you want is that, okay, so one thing that you must remember is that whenever you are trying to do a receive, okay, typically speaking, okay, there are again differences, we will talk about it little later on. A process which is executing this receive cannot go past this receive unless it has received the value. And when would it receive the value? Only when process 0 has sent it. And when process 0 has sent it, when this process receives it, it knows that it has to do one more iteration or it does not have to do one more iteration, correct. So, it is ready to go. It does not have to worry about whether process 5 has received this value, process 8 has received this value, process 15 has received this value. It does not care about it. Process 0 has told me that I can go ahead, I will go ahead. Okay. That kind of an asynchronous execution could happen because I have received the go ahead from process 0. There is a synchronization with process 0, right, but that is all that I need. Process 0 is the one who is telling everybody to go or not go, right. As soon as I have got that thing, I can go, right. I can go and I can start executing, but let us say that I am process 3. I have got the message, process 4 has not got. What is the implication of that? The implication of that, you are supposed to receive a row from process 4, this thing. You are not going to receive it if that has not got the done signal. So, eventually you will wait for, if you are process 3, you will wait for process 2 to get the done signal, you would have waited for process 4 to get the done signal. They both have to come to these respective sends and send you something. After that only you can go. Likewise, you will also send some data to those, but you do not necessarily wait for them to receive, you can actually go, because send is one way. So, you can just send it and then you can start going. Again, there are variations in that. So, essentially if you look at it, each process is more tightly synchronized with process 0, PID minus 1 and PID plus 1. It does not necessarily care about PID plus 100. Okay. But if you put all of these things together, it is not that one process is going to go very fast while the other process is 10 iterations behind. That is not going to happen. Eventually, all of them would be in the same convergence iteration. Okay. That is really how the overall synchronization is achieved by locally synchronizing. Okay. Good. So, let us move forward. We have a lot more things to cover. As I mentioned earlier, one could have used reduce. Okay, one could have used broadcast to communicate the values instead of individually communicating. We will see examples of this. Okay. All right. So, now what we are going to do is that in the next 30 minutes or so, we will very quickly see, okay, overview of OpenMP. Okay, OpenMP is the standard for shared memory parallel programming. Okay. And it is basically an application program interface which tells the standard C or Fortran program, okay, what can be done in parallel. Okay, and this it tells by means of what are called pragmas, okay, which are what is called compiler directives. Okay. Those compiler directives tells this part of the program can be executed in parallel, this part of the program is a critical section, this variable is a shared variable, this variable is a private variable, and so on and so forth. So, you take a OpenMP program and compile it for your, let us say, sequential processor without the OpenMP, it will still run because all these pragmas are going to be ignored as comments. If you compile it with the OpenMP compiler, these directives are taken and appropriately compiled. Okay. So, that is the main thing. These are APIs, compiler directives, and depending on these compiler directives, your code is going to be compiled and appropriate runtime library routines are going to be linked to that, and of course, you will use the environment variables to run them. Okay. So, OpenMP itself follows a model which is what is called a fork join model. By that what we mean is that initially there is one master process which will be executing, and then whenever it comes to a parallel section, it will fork a number of threads, okay, a number of threads, and that will also, the master process or master thread will also continue to execute. So, it will essentially fork n minus 1 threads, and that also will continue to execute. So, all of these n threads will execute in parallel. Okay, it is a multi-threaded programming model. So, n threads are going to be executing in parallel, and it will have some kind of an implicit join or an explicit join, where it will wait for all of these threads to complete these tasks, and only when all of them have completed, right, you can proceed, and after that only the master thread will start executing the program. All other threads will be idle. Again, if you see one more fork, right, and depending on the number of threads that have to be executed there, you will see that that many threads will again execute, again join. If you do not do anything specifically, what happens is that in all of these cases the number of threads will be the same n, but there are possibilities by which you can even change it. Okay. So, essentially OpenMP is a programming model which is what is called a fork join programming model. Okay. It allows you to do both domain decomposition as well as task decomposition. Okay. So, if each one of these tasks is an independent task, different computations, right, which you can do using the OMP sections command, which I will show you, then that is like a task decomposition. Each task is doing something very different. Okay. If I kind of divide the data and then ask n of my threads to execute, like what we did in the Jacobi example, that is domain decomposition, right, which I can do using a parallel for statement, okay, that is data decomposition. So, you can do both data decomposition, domain decomposition, and you can combine both of them in a single program. So, that is the advantage. Okay. So, we call this thread as the master thread and all of these other threads as the worker threads, and these are the parallel regions which are kind of identified or which are kind of indicated or specified by the programmer using appropriate directives. Okay. So, as I mentioned earlier, most of these commands are pragmas, okay, and it is typically written in this form, you know, hash pragma OMP something, and it can have optional clauses added to that. Okay. And then this construct applies to a structural block, and a structural block is basically a structured block that you see in your C or C++ program, right, one with curly braces, right, or the single statement that are below that. There are 5 different categories of OMP constructs. We will see one example for each one of them to teach OpenMP itself, and OpenMP is currently in version 4.5 plus, okay, and to teach that itself would take a full day. So, we do not have that kind of a time. So, we will have a quick sampler of that, okay, that is really what you are going to see. Yeah. OpenMP. So, there is a OpenMP compiler which you can actually use. Actually what happens is that your normal GCC will compile your OpenMP program. It will attach appropriate libraries to that. Okay. These are pragmas. You will do the exercise today in hands on, right. Okay. So, here is a quick example, right. So, pay attention to this. So, we have a okay, it does not really matter here. So, let us look at this. So, here if we say hash pragma OMP parallel, okay, and here there is a command which says set number of threads 4. What does it do? 4 parallel threads, this is easy to understand. And then we are going to say that this particular structured block is going to be executed in parallel. So, all the threads are going to execute them in parallel. What is that they are going to do? Each one is going to get ID, which is basically what is its rank or PID, okay, and then it is going to call this function poo, which could be something like a print function or could be any other function, okay, with that particular ID and maybe this array, which is a shared array, right. Okay. So, let us see. So, that is I have explained all of these things, right. So, this is a runtime function to get so many threads, and then all of this is executed in parallel, and this essentially gets you the PID of that particular thread or process. Okay. So, we said that because of this hash pragma, this poo function is going to be called 4 times, because there are 4 threads, and each time it is going to be called with a different ID value from 0 to 3, which is the PID value. Okay. So, if you look at it pictorially, this is what is going to happen, right. The master thread executes, it declares this variable, and if there are any other statements here, only the master thread will execute. Then the master thread says that I need 4 threads, that means that apart from me, I need 3 more threads, okay, and all of us are going to execute this, and I am going to do print, and remember that this pragma OMP parallel is only for this structured block. So, the print is going to be executed only by the master thread, and whenever you have a pragma OMP parallel ending, there is an implicit barrier there. That means that when I come to this statement, I can execute this statement only after all of these threads have completed executing the function poo, right. So, there is an implicit barrier at the end of this statement, and with this implicit barrier, supposing let us say the function poo modifies the variable modifies the variable a, right. The changes made by all of these things, okay, will definitely be visible here, because you have a synchronization here, barrier synchronization here, right. All of these things would have done their writes, okay, and all of those writes will definitely be visible, okay. In a sequential consistency model, they will all be visible, okay. In some other relaxed consistency model also, they will all be visible because of this barrier synchronization, okay. So, there is an implicit barrier. Whenever you do a parallel OMP parallel, okay, that structured block is forked, and this is the implicit join, and at the implicit join there is a barrier. Okay. Okay. All right, I have already explained those things. Okay. Here is another example, right. Same code, but now I have replaced poo by a print function. Okay. So, what is going to be printed? Let us assume that it is going to be printed on your terminal, right. So, on your terminal, what is it going to print? Hello world 5 times or 4 times? 4 times. With hello world 1, hello world 2, hello world 3, hello world 4, any order, very good. So, that is really what is going to happen, right, because you can't guarantee in what order these print statements are going to be executed. Okay. They all are being executed by these 4 threads concurrently, they will happen in some order. What about all done? Can it happen before any of these things? No, it has to happen after all of these things have happened. Okay. Good. Okay. So far so good. Okay. So, as I mentioned earlier, there is an implicit barrier here. The master thread waits for all these other threads, worker threads to complete, and only when it knows all of these worker threads have completed, it will go to the next statement. So far so good, but let us see some domain decomposition. Yeah.
Out of all the numbers, can we know which ID corresponds to the master thread?
Typically, it will be 0. Okay. Again, it depends on the implementation. Okay. Now, let us say that I have this code. What we learnt in our parallelization technique is that if I want to, so this is a very simple code, A of I is equal to B of I plus C of I, vector addition, correct, and each element of I, correct, can be done independently, there is no dependency, right. So, if I have an array of n elements, I can do the first 10 elements by one process or one thread, the next 10 elements by one thread, the next 10 elements by one thread, and so on, correct. That is really how you would parallelize it. So, if you want to write a program, you can actually write a program, which is what I call a semi-manual parallelization, okay. That is manual, well actually it is manual, but semi-automatic or whatever. So, what I have done is that I say basically ID is basically number of get my thread ID, and then I do something here. What I do is that I divide the total number of elements by the number of threads. Okay. So, this gives me my PID, this gives me the total number of threads, okay, in the program. So, that depends on the environment variable or wherever you have set it previously. So, you are going to get that number, and then you are going to basically say that I am going to start from n divided by n thread multiplied by my ID up to this particular value, which is basically the start point of the next thread, and I am going to do all of these things sequentially within that thread, and all the threads would do these things in parallel, right. Of course, I have to put those pragmas. So, I have already put the pragma, I am sorry, I have already put the pragma OMP parallel. Okay. So, all of this is going to be executed by, let us say, the 8 threads or the 4 threads that you have in your program. Okay. Each one is going to do some parts of the array. So, this is essentially domain decomposition. Yes. You need to give the number of threads in some place. You can set it in your environment variable also, okay. And if you do not do any of these things, OpenMP will do a default number, and that depends on the implementation, okay. You know for this program I want to use this many number of processes. So, you will mention that, correct. So, you will do. Okay. Now, what you can do is that instead of doing all of these hard work trying to find out how to divide this, whether I do, right, a block allocation, a cyclic allocation or a block cyclic allocation, and see whether the performance that I get is good or not good, etc., right. I can simply use the OMP parallel for, right, the OMP for schedule, right. Now, this code becomes as simple as this. If you are, in fact, if you look at it, this is your sequential code, that is how you started off with, correct. And all that you have done is added these 2 pragmas to it. This pragma says it has to be run in parallel. This pragma says that this is a for loop which you have to split, okay. You have to do a domain decomposition, and the domain decomposition that you do here is a static block, right, block of rows, block of elements, block of columns, whatever it is, static block. Of course, this is an optional parameter. You can again change this parameter or value to something else, some other class also. I will show you that in the next slide. Okay. Supposing let us say we have 1000 elements, right, and we have 10 threads. We could have divided each thread and given 100 elements, right. Then you would expect all of them to be finishing at the same time. So, when you come to this end of the structured block, there is an implicit, right, implicit join or an implicit barrier there, and that barrier would make sure that all of them have finished, and then you can go down further, correct. Do you see any problem here? The underlying assumption is that all these threads which are running in different cores or different processors are executing more or less at the same speed, correct. And here we have some skeleton code. This code could have been complicated, this code could have been more work for some rows, less work for some other rows, whatever it could have been, correct, possible, right. Or some processors may be fast, some processors may be slow. So, if I just split it evenly, right, and I give it to all the processes and then do a join or a barrier here, my assumption is that they all take more or less the equal amount of compute time. That is when I am efficient. If some takes more time, some takes less time, the faster person would finish very early, okay, and he will be idle, while the slower person taking a long time to do, in which case I could have actually distributed more rows to the faster person and less rows to the slower person. I could have done that if I had known that, correct. So, are there mechanisms for doing that? Okay, that is the next question to ask. Okay. Right. Well, just one second, hold on to that question, we are going to come to that, but before that let me just show a very simple, this is the code that we saw in the last slide, okay. And what we can also do is that we can combine these two pragmas into one pragma, which is OMP parallel for, okay, that is just a simplification, right. So, that is fine. We are going to now talk about the static, but before we do the static, let us just talk about the following things. So, when you do static, you are going to give these blocks of rows or blocks of elements to different processes. And the right thing to do, of course, is that assuming that all your processors or cores are identical, would be to give equal amount of work to everybody, and that is why you static. So, if you do not specify static, by default it is static. That is the right thing to do, divide the work equally across all of them and then give it. Okay. So, essentially what it is going to do is going to divide this evenly, but then what it is going to do is that it has a default chunk size. If you do not specify the chunk size, it is going to assume a default chunk size, number of blocks. So, it is going to take the first chunk, give it to thread 0, the second chunk give it to thread 1, third chunk give it to thread 2. Okay. But let us say you have more chunks than the number of threads, and will again go back to thread 0, thread 1, thread 2. So, it is basically what is called a block cyclic allocation, right, a block of rows allocated to each thread and then that is done cyclically. Okay. Again, the idea is to make sure that we spread the work as evenly as possible. Okay. If the number of rows is too small, smaller than the chunk size, then you do not really worry about it. This is not a program which is worth parallelizing. So, let us not even worry about it. Okay. But then the problem comes if your processors, some processors are fast and some processors are slow, some cores are fast, some cores are slow, or some cores have more work to do in terms of the rows which have been assigned than some other cores, right. Now, let us hear your question. Your question. No, you decompose the problem irrespective of whether it is static or not. Your OMP parallel itself will actually, OMP parallel for will actually decompose. OMP parallel for schedule will decompose your task domain decompositor. Static tells you how to do the domain decomposition. Okay. Static tells you that you divide this in terms of chunks and keep each chunk to one thread and do it in a round robin fashion. That is what static tells you. No question is stupid question. Okay. You can ask a question.
In processors, then the thread numbers is actually corresponds to each thread from each processor.
Each thread.
From each processor.
Okay. Let us not worry about how the thread gets mapped to a processor. Why is that important? Let us say if thread I gets mapped to core J, what is the problem? No problem. For each core we have a different thread, yes. Okay. Again, you should be very careful here. Let us say that you wrote the program when you were here, okay, for the server which had let us say 16 cores. So, you said number of threads equal to 16. Tomorrow you go back to your college, right, there you have a server with 8 cores. Now, you try to run it on that particular server, what will these 16 threads do? You said that all of these 16 threads have to execute in parallel, but you have only 8 cores. So, the underlying system will map 2 threads per core. So, that is not in your control, the OpenMP environment will control that. The OpenMP runtime environment will control that. That is why we do not need to worry about where the thread runs. So, it does not matter whether thread 5 runs in processor 5, okay, or thread 5 runs in processor 10, or thread 5 along with the thread 10 runs in processor 7, I do not care. As far as I am concerned, they are all executing in parallel. Okay. If they have enough cores, they will all be in different cores. If you do not have enough cores, they will be squeezed into the available cores. If you have too many cores, some of the cores will sleep, right. So, we do not have to worry about that, the OpenMP environment will take care of that. So, that is why when you write, you always think, okay, it is better to parallelize this program into this many number of threads or this many number of tasks. Okay. That is actually the right way of looking at it. Okay. Now, if the computation is not balanced because the processors are of different kind or the works that are given to different processors are different, then static will fail badly, because the fast processor will compute quick and the slow processor will take more time. The fast processor will be idling while you have more rows of, more work at the slower processor. So, the dynamic situation, so okay, but then let me see, okay. So, essentially what we need to do is that we need to do load balancing, and we could have done load balancing by dividing these tasks into finer granularity, okay, and then allocating them to tasks and then maybe doing some kind of a dynamic load balancing among them. But the more finer you divide, then there is more overhead that you will incur. This is what we saw when we talked about decomposition and assignment. The same argument is what is being put in here. You have to get into certain levels of granularity and then divide them. But more importantly, you should also have certain mechanism to do dynamic scheduling if the work itself is inherently not load balanced. Okay. You may not know at compile time, or you may not know when you are writing the program that each one of these process or each one of these subtasks is going to take identical amount of time, because sometimes there may be some if conditions which will determine the amount of work that is to be done within a thread. Okay. In such situations, it might be beneficial to use the dynamic schedule, where what you do is that you again decompose the array in terms of chunks, but this time what you do is that you will assign chunk 0 to thread 0, chunk 1 to thread 1, chunk okay, let us say 8 to thread 8 and so on, and then you stop as soon as the number of threads is over. Okay. You may have additional chunks with you, but you will not allocate it to them, allocate it to any particular thread. So, let us again take an example. Supposing let us say we are doing the same 1000 elements. Okay, I am going to divide this in chunks of let us say 10 instead of 100. Okay, so, there are 100 chunks that I have. Let us say I have 10 threads. So, I am going to allocate chunk 1 to thread 1, chunk 2 to thread 2, chunk 10 to thread 10. I will say go execute your chunk and then come back and tell me, right. As soon as you are finished with your chunk, I will give you more chunk. Right. So, now what happens is that I have this pile of tasks, I ask each one of you to take one work, complete it, and when you finish you can come and take the next task, correct. Static I allocate a priori, I gave you okay, I have let us say I have 100 assignments to correct, right. There are 50 people here. One thing is that I could have given 2 assignments to each one of you. That means that until you finish those 2 assignments I can't do anything. Other one is that I give each one of you one assignment, whoever finishes can come and take the next assignment. Let us say you take 30 minutes to grade, he takes only 10 minutes, then in that time he would have graded 3 assignments. No, static a priori gives it to you, a priori gives the tasks to the threads, whereas dynamic allocates the task only after it completes one of those chunks. Okay, that is the difference. Okay. So, typically it will be a good idea to do dynamic, but if you do dynamic on a simple loop where everything is equal, you may end up with some additional overheads because of this additional coordination. So, you have to use the right thing. OpenMP essentially provides you those handles for you to use the right one. Okay? Fair enough? You are all liking it, right? See. Okay. Now, this is the way by which you can do task decomposition in OpenMP. I can define individual tasks. I do x calculation here, I do y calculation here, I do z calculation here, and I want this x, y, z calculation to be done in parallel by 3 threads. Okay? So, I define them in terms of OMP sections, and then I put a OMP parallel and OMP sections there. Of course, you can combine this and then say OMP sections, parallel sections or something like that. OMP allows you to do all of those things. But the idea is simple. Now, x, y, z are going to be computed in parallel by 3 threads. Okay, one of them might be master thread, the other might be the other 2 threads. Okay, and this is not necessarily domain decomposition. X could be some independent computation, y could be some other independent computation, z could be some other independent computations, and they may all work on the entire data, entire shared data, correct. Whereas in domain decomposition, you are working only on a subdomain, my block of rows, correct. That is not the case here, right. So, that is essentially what OpenMP allows you to do. Okay. I am sorry. Again at the end, oh, I skipped so many slides. So, at the end of a OMP sections, there is again a barrier synchronization, right. That essentially tells all of these threads must complete their computation before the master thread can proceed further. Okay, let us take a simple example, calculation of pi. Yes. OMP sections. See, if you have, again idea is very simple, right. If you have more sections than the number of threads, it is going to be distributed to the threads. If you have less sections, then fewer threads are going to be used, right. Oops, I should not do this, I should not back there. Okay. Let us do a simple pi calculation program. Okay. Essentially here what you do is that you try to compute the area in the circle, maybe in the first quadrant. Okay. That is really what you try to do. You take small strips, okay, and then you compute the area of these small strips and then you add them up. Okay. So, there are these equations which you are familiar with. I do not have to go through this. This is the first program you would have written in your C or right C language or Java or whatever it is. That is the same program over here. Okay. That is a sequential computation, right. You do it for a number of steps, and the smaller the width of the strip is, right, the more accurate your pi value would be. That means that you would have to have a very large number of steps. So, for example, here I have taken 100,000 steps, right. The nice thing about this is that this part of the computation where you are doing, okay, x and then maybe even calculating this value, it could be done in parallel. Okay. It could actually this all of these 100,000 operations can be done in parallel, but of course, you will group them into some. So, let us say if you have 100 threads, then you can say each one of the thread can do 1000 steps, right, and they can actually do something like that. You will do 100 such things, and then of course, you can globally do the reduction. So, there is a reduction that is involved in here, that is accumulation of values. So, this part of the computation can be done in parallel, okay, and this part of accumulation can be done locally, serially, and then globally it has to be reduced, correct. That is the whole idea. Got it? Any questions? Right, we are going to see how this program is going to be written in OpenMP. Okay. Let us just assume that this sequential program is given to us and it is correct, right. Let us not question that, right. Okay. So, there you go. So, what I am going to do is that I am going to set the number of threads. Okay. So, if you want 100 threads, you say basically you want 100 threads, put OMP parallel, okay. Then there is a OMP for. So, this loop is going to be domain decomposed, all right. This loop is going to be domain decomposed. Okay. I am doing one small thing here, I am going to declare this variable. So, if you go to the previous page, right, sum was a scalar variable, correct. Sum was a scalar variable, x is also a scalar variable. Okay. By default, all the variables that are declared in your OpenMP program are shared variables. If you want them to be private, you have to explicitly state it. Okay. So, let us see what happens here. I have now changed my sum to an array. Okay. Maybe sum, let us see where I have declared sum. I have not? Okay, good. Huh? After, no, tell me which number of, which line? Fifth line, okay, there you go, there you go, right. That is where I have declared my sum to be an array and I have initialized it to 0. Okay, that is good. let's not okay. So double x. Okay. So let's not too much worry about x at this point in time. We'll come to it little later. Okay. So now what happens? This parallel loop, okay, is going to do it for 100 threads. Each thread is going to do 1000 elements, right? There is no problem with that. Okay. And it is going to compute this value and then add it to that particular element of sum. So, thread 1 will add it to sum 1, thread 2 will add it to sum 2 and so on, correct. And because each one of them is an individual element, there is no problem with regard to synchronization, there is no problem with respect to some other thread writing into that value, because thread 1 is only going to write into sum 1, thread 2 is only going to write to sum 2 and so on. So, there is no synchronization that is really needed here. Okay. Then there is this step where I am going to do for I is equal to 1 to number of threads, the value of pi, which is basically the sum of all of these sum I multiplied by the step size, okay, which is what I need to do. Okay. That is being done here, but this might require some synchronization, because pi is a shared variable and I am doing this update to pi, okay, read and increment, okay, read and modify, read modify kind of a write. When I do, I have to do some synchronization. Okay. Let us see how we can do that, but one, okay, yeah. So that part of it we have not really discussed, we will come back to that later. But it is fairly obvious that this does not require any synchronization, because even though sum is a shared variable, each one of these threads is going to be writing into one individual element, and therefore, there is no synchronization that is needed here. Okay. Let us move forward, because I really need to talk a little bit about OpenMP and about MPI as well. Okay. So, as I mentioned earlier, most variables are shared by default. If you want, so all the global variables are shared, and there is one other thing which is kind of skipping. Then you can also declare private variables by using the private command. Okay. So, those are the private variables. This is how you declare it. When you say private, that variable is local to that thread. Okay. And when you say private, and when a master thread is executing and then after that you fork all of these threads, that private variable will not have an initial value. If you want it to have an initial value which is same as the master thread, then you will use what is called the first private. And similarly, when you want the thread values to come back to the master thread, okay, so this is like the value being passed from the master thread to all the threads, you use first private. Similarly, for the last value of the thread to go to the master value, then you will use something called, oh my goodness, my thing is skipping fast. There is a last private which is not appearing here, which is not appearing there. Sorry, there is a problem with the animation. Okay. So, there is a first private and there is a last private declaration that are possible. Okay. So, as we mentioned earlier, whenever you are doing this read modify, you have to make sure that there is synchronization, otherwise the values that you are going to update may not be reflected properly. So, in order to do these kinds of synchronization, OpenMP allows you to define critical sections, it allows you to do atomic updates, it allows you to do barriers, and of course, it allows you to do a bunch of other things which I am not going to discuss. Okay. So, for example, you can define a critical section using pragma OMP critical. Okay. You can also define something as atomic and so on, right. That is how you define OMP, pragma OMP atomic, and then you can put pi is equal to pi plus something, right, that you can define it in the atomic section. Okay. You can also do it using reduction. MPI allows you to do reduce, okay, and reduction is specified in this way, and I should have the pragma for OMP reduction. Okay. Then when you do OMP parallel for reduction, you do not have to worry about my local variables, global local reduction, global reduction, etc. You can just entirely leave it to OpenMP to deal with it the most appropriate way. Okay. So, it provides you all of those options. Reduction is basically doing some accumulation. We use the word reduction to do something like this, saw the example, right. So, for example, here this operation sum is equal to sum plus, right, that is basically what is called a reduction, right. You want to accumulate all of these values and you have to do it carefully, because if you are doing it on a shared variable, synchronization has to be done, and you do not want to do it sequentially, because that will take you more time. You do not want to use atomic, because atomic is essentially sequential. So, what you want to do is that you want to do some kind of a local reduction and then a global reduction. The global reduction is done using atomic, the local reduction is done in parallel. The same thing that we discussed yesterday, right. That is exactly what it is. But if you leave it to MPI and then use this OMP parallel for reduction, it will do it the optimal way. Okay. It will possibly do some local reduction and global reduction. Okay. I will not go into this example, I will just skip this. You can do barrier synchronization, which is what we talked about, right. To ensure that all of these things have come to that, you can do barrier synchronization. Okay. So, here is here is some example. So, again I have a OMP parallel and then say do certain computation. Okay. So, all the threads will actually do this computation in parallel, and then I can do OMP atomic, I can do the summation where I do the reduction, and then again I go back and then say OMP barrier, which means that after all of these things is done by all the threads, okay, I want this computation to be performed. So, that is really how you specify these things. Okay. By the way, as we mentioned earlier, at the end of a parallel or at the end of a OMP section, okay, there is something also called single, there is an implicit barrier. Remember, we saw whenever there is a OMP parallel, there is an implicit barrier. Whenever you have a OMP section, there is an implicit barrier. Okay, there you do not explicitly say, but if you want to say explicitly, you can also have that. Okay. There is also a class called no wait, which makes that the barrier is not enforced, that is also possible. These are some additional constructs in OpenMP. I am not going to deal with this. Each one of them, you can see that this is setting the number of threads, this is getting the number of threads, this is getting the thread number, and so on and so forth. Okay. So, you can actually read up about all of these things in the manual, but what I have discussed so far, you can actually use it to write meaningful parallel programs, and in fact, in today's hands on, I have even given you that parallel program, OpenMP parallel program. You have to run it and then you can change the number of threads and see what is happening, right. But please put in some time and effort to see what happens if you change some parts of the code. If there is a reduction there, replace it by OMP reduction. If there is a OMP reduction, replace it by your own code and then see how the reduction is getting performed. If you do not put synchronization, see whether it really messes it up. Okay, executes it a number of times and then see whether in fact synchronization is required or not required. Okay. So, try some of these variations and then have a feel for it. That is essentially what today's hands on is all about. Okay. So, I have another 15 minutes where I am going to quickly talk about MPI. So, MPI is message passing program, right. In fact, in your hands on session today, the Jacobi program that we have discussed, I have given you the OpenMP version. So, do not think that I wrote the program, my student wrote the program. Okay. So, I am going to give you that program, you can actually inspect that, you can change whatever you want and then see what is happening, right. Okay. So, similarly, I am going to also give you MPI assignments. So, let me just very quickly introduce MPI in the next 15 minutes or so before lunch. Okay. So, again MPI is a standard API for message passing programs. Okay. The hardware does not have any shared memory. So, interaction happens by means of these send receive messages, and typically MPI is implemented as a library. So, therefore, when you compile your C program, you have to include that library in order for you to be able to use those send receive calls. Okay. So, essentially this is what happens here. If you have a standard network, which is the hardware, okay, that implements, on top of that you have the standard TCP IP, then on top of that this MPI library is implemented, and your application essentially calls these APIs, application program interfaces, and does send receive. If you have a custom network, then of course, there is some kind of maybe a custom software which is implemented for, and then on top of that MPI is implemented. So, this is how it would look like. We will not have to worry too much about this. So, you compile your programs by linking it with the MPI library, and then that is basically MPI.h, and you create these processes. Again this is called SPMD, single program multiple data. So, all the processes which are going to run, okay, they are identical. Okay. So, if you want some process to do the master process work and some process to do the client processes work or the child processes work, then you have to identify it by means of if my PID equal to 0, else something, right. So, that kind of a thing is going to be there. So, but the code is the same for both of them, right. When it is running, it will understand that it is a master process or it is a slave process, and it will execute the appropriate piece of code, right. So, one executable, multiple instances are invoked on these different processes, different processors, okay. And of course, you use what is called the MPI run, and therefore, the underlying parallel environment would make sure that that many processes are forked in these things. Okay. All right. So, these are some of the commands. Let me just quickly show them first. Okay. I am not going to deal with all of them. Okay. We are often going to go with our intuition what these would mean, and then find out if it is required more about them. Okay. I will introduce this MPI send receive commands which are critical. I will introduce some of these other commands which are called barrier or broadcast and so on, and maybe some basic commands in MPI rank and MPI init. Okay. That is basically what I would do. Okay. Oh, okay. So, first let us talk about the MPI send and receive, right. The send command, the sender is going to specify who the destination is. Remember the program that we saw with regard to the message passing thing, and some of you were questioning, what is this row, what is this tag and so on. So, we are going to discuss those things now. So, it typically specifies the destination and a tag, okay, which kind of identifies what communication is this, what is this communication for, and the address from where the data has to be sent, and the amount of data that has to be sent, and the type, whether it is a character, integer, whatever it is, right. All of this it is going to specify. So, the MPI send command is essentially going to take data from this address. How much of data is decided by a combination of these two things, okay, and it is going to be sent to this destination. In fact, it may be sending multiple messages to the same destination, in which case which data to match with what send and what receive is determined by this tag. For example, process 0 may be sending 2 messages to process 1, okay. One may be the done flag, the other may be let us say some other variable. So, it has to know which one is what, right. So, that is distinguished by means of this tag. Okay. So, you can specify, okay, I am going to send a done variable now, I am going to send this one, because messages may be received in the receiver out of order. So, you do not want to kind of say, okay, whatever is in the top of my thing I am going to match it to done, that is not what you want to do, right. Of course, in situations where you do not care about the order, you could also use, if you are going to send only one message, then you can just say tag is any, does not really matter. Okay. So, that is really what tag is about. In the initial cases, we will kind of use some common names for this and be done with it, but if you are writing more complicated programs, you can actually use these tags to do certain things. The receiver actually specifies the source where it wants to receive the data, the tag, okay. I am sorry, the source from which it wants to receive the data, the tag, and the location where it wants to receive the data. So, whenever you are receiving let us say the done variable, you have to say I am going to get the done variable, it has to be put in done in that location. So, that you specify here, or I am going to receive ghost row 0, I am going to receive ghost row n plus 1, that you specify over there. Okay. Then the size and the type of data. Okay. Receiver can also need not have to specify these things exactly, sometimes it can use wild cards like I want to receive it from any source who is sending it. Your program may kind of work in that mode also. Again, these are some advanced features, we will not worry about it. Okay. The send receive themselves have several variants. Okay. You have the standard send, you have the buffered send, you have a synchronous send, you have the ready send, and you have similar versions for receives also. Again, it could be blocking or non-blocking. Sends and receives could be blocking or non-blocking. Blocking means whenever you are executing a send command, you will come out of the send command only when something is completed. Okay, I purposefully say something. You could have said that why didn't you say that when send is complete? No, I said something is complete, because send involves two parts: copying the data from the user address space and sending it to the receiving node. Depending on how I define which send I use, okay, and how I do this copying, it varies. Okay. So, there are, as I mentioned, there are several variants and one has to study these variants carefully. In the simple form, right, whenever I use a blocking send, it comes out of that send when the data is being copied into some buffer. As soon as the data is being copied into that buffer, the send will come out. Whereas, in the case of a receive, okay, if you have a blocking receive, it will come out of the blocking receive only when it has received the data from the destination. If you have a non-blocking receive, then what it means is that you are saying in which location you want to receive the data, and you do not want to necessarily wait for the data to arrive, but you want to compute some more computation before the data comes in. But when you want to wait for the data in that location, you will use some kind of a wait command, MPI wait command, to wait for that. So, a combination of non-blocking receive and a wait would actually implement blocking, but the advantage here is that by the time you post the receive and the time that you wait, you could actually do some additional computations in between. That's the advantage. Okay. So, there are different variants. It is not possible to cover all of them in 1 hour's lecture. So, we are not going to see all of them, but we will see some flavor of that to get an idea. Okay. Again, there is the standard send, in which case what happens is that when you do a send or receive, right, the underlying environment will copy it into an internal buffer. Okay. And that is essentially what the standard means. When you say buffered send or a buffered receive, there is an explicit buffer that the user specifies in which it is first copied. Okay. There are certain restrictions on that. Okay. The synchronous send receive is a very interesting send receive. When you say a synchronous send, it actually waits for the receive to receive it, and it will come out only when the receive has received it. Okay. So, when you use standard send or buffered send, it is not necessarily synchronous. That is why I said that when a send is complete, it completes certain actions and then it can come out. Okay. So, one has to use these things carefully, because if you do not use these things carefully, you could end up writing a program which could deadlock. Maybe process 0 has sent a synchronous send, okay, saying that process 1 will receive the data and then I will get it, and process 1 thinks that okay, I am also going to do a synchronous send, and they both are trying to do a send to each other and nobody is willing to return. Then you could end up in a deadlock. So, you have to be careful, and that is where you need to know the semantics of these send receives correctly. Okay, for now we will not worry too much about it. So, an MPI send is going to look like this: the locations from where you want to send the data, the amount of data, the data type, and the process to which you want to send the data, the optional tag, and there is one more thing called communication group. Okay. For now we will assume that everybody is in the same communication group. You can define actually subgroups, and you can do communications within the subgroup and so on and so forth. Okay. For now we can just put some value for this and be done with it. Okay. So, as I mentioned earlier, blocking and non-blocking. Blocking means that as soon as you complete some local action, you can come out. Non-blocking is that you can actually return immediately without even completing that. Okay. There are these. So far when you look at MPI send and MPI receive, there is basically one-to-one communication. Process I wants to send a message to process J, or process J wants to receive a message from process I. So, this is basically what we call as one-to-one communication. You can also do group communication, okay, which is something like a broadcast. Okay. Let me just quickly go to that. So, you can do a broadcast, or you can do a multicast. There are also other commands like scatter and gather. Reduce is another form of, right, a group communication. And again, each of these group communication can be restricted to a communication group or can be restricted to the entire set of processes. So, those options are possible. Okay. So, broadcast is essentially that you want to send a value to all the processes. Remember the done flag? We were earlier communicating to each one of the processes individually, doing a send, okay, one-to-one send receive to each one of those processes. We could have avoided that by simply making sure that all processes execute a broadcast, while process 0 will actually send the data and all other processes will receive it, right. That is easier to think in terms of. Similarly, there are scatter, gather, different types of operations which helps you to accumulate data from multiple processes. I will not go into those details. Again, we come back to this Pi program which we discussed earlier. In the MPI format, it is going to look like this. Each process is computing, okay, for a given number of strips, right, and it is computing the local accumulated value. Okay. So, all of this is being done in parallel. You can see that before you start the communication, there is an MPI broadcast where the master process states how many steps you have to do. Okay. So, that is where the master process determines each one of these processes needs to do 1000 steps. So, it tells that, or each one of these things needs to do 100